So here we're asked to consider some complex numbers. We're given Z1, Z2, and Z3, and we have a series of questions that we need to answer using them. So the first one is to find Z1 multiplied by Z2. Alright, so looking at Z1 and Z2, they're both in the same form, i.e. Cartesian form. So it's probably just going to be easiest to use them as is and multiply together. So subbing them in. And multiplying out, we get 3 times -1, which is -3. 3 times 3i is positive 9i. 2i times -1 is minus 2i. And then 2i times 3i is going to be 6i squared. Alright, so to simplify this, we know that I squared is equal to -1. Alright, I being our imaginary number. So we can write this as -3. I may as well put these together, so it's going to be 7i. And then this is going to get replaced, so it's going to be 6 times -1. So this is like -6. And then if we put that with the -3, that's going to leave us with -9 over all, plus the 7i. So that there would be my answer to part A. Alright, so up next is B. We want Z1 multiplied by its conjugate, which is what the bar over the top means. So if we write out Z1, it was the 3 plus 2i. Its conjugate is when we flip over the sign on the imaginary part. So this would become 3 minus 2i. So what we want to do is multiply these together. So one way that we can do it is to just sub them in like before and expand it out. So we would get 9 minus 6i plus 6i minus 4i squared. And what we see happening this time is that the imaginary parts cancel out with each other. So we've got -6i plus 6i, they're going to disappear. And we're left with 9. Remember again, we can use our I squared equals -1. So this is going to become minus 4 times -1. This becomes positive 4, so 4 plus 9 is 13 as our answer. The other option that you have available is that when you do this calculation, you're always going to get out the components squared and added together. So kind of the shortcut way would be to say that this is going to equal 3 squared plus the 2 squared. So the component in the real direction and component in the imaginary direction. So that becomes 9 plus 4, which is 13 as well. So either way, you get the same answer. Alright, so part C is that we want to find the modulus of our Z2 complex number. So just as a reminder, Z2 was equal to -1 plus 3i. So the modulus of it, it's like finding the magnitude of a vector. It's going to be the square root of our two components squared and added together. So I should probably write this technically as -1. And this one, this component, is 3. So here we're going to get 1 squared, -1 squared, which is 1, and then 3 squared, which is 9. So we end up with our answer, which is square root of 10. Alright, next one. We're up to part D, which is to convert Z3 into polar form. So if we look at Z3 at the moment, it's given in the exponential form, So yeah, we're going to need to swap this over into polar. Alright, so jumping down. So Z3 was 2e to the I pi. And in exponential form, the general form is like re to the I theta. So that means that we've got an r of 2 and our theta is equal to pi, just by directly equating those. So when we want to go and write it into our polar form, the general version is r outside of cos theta plus I sine theta. So we just need to substitute in these two values. So r becomes 2, cos becomes pi, theta becomes pi, and theta becomes pi again. So that there would be our answer for that complex number in polar form. Alright, so next up, it asked us, I think, to convert now Z3 into Cartesian form. So that's where we need to write it like these other ones were, with like a real component plus an imaginary component. So jumping back down, we should be able to kind of continue off what we had for the polar form. So basically, if we just solve this, like figure out what cos pi is and sine pi, and multiply by the 2 out the front, we're almost there, yeah? We're going to get a real part and an imaginary part. So let's figure out what cos of pi is. If we draw ourselves a little graph of cos, we know that cos starts at 1. All right, and one cycle of it goes to 2 pi. So if we're interested in pi, that's going to be halfway, which I'll pop here, and it cycles between 1 and -1. So at the bottom here, it's going to be equal to -1. So therefore, cos of pi is -1. So we can pop that in here. And then we need to do the same sort of thing for sine. So if we draw ourselves a sine curve, so we know that sine starts at 0, and one cycle of it again goes to 2 pi. So that means that pi is going to be halfway. And we can see here it's crossing the axis at that point. Let's mark that in red. So therefore, sine of pi, we can read it off as just equal to 0. So we're going to get I times 0 in here. So now let's multiply in our 2. So it's going to be 2 times -1, which is -2. And I times 0, that disappears, and you know, it could get divided by 2 again, but it doesn't really matter because it's going to go to 0. So our answer in Cartesian form is just that Z3 is equal to -2. Alright, so we've got our very last part of the question, which is it wants us to draw Z1, Z2 and Z3 on an Argand diagram. So I might just do that here. So setting up our Argand diagram, we've got the real on the horizontal axis and the imaginary on the vertical axis. So if we look at Z1 initially, it's 3 on the real axis, so let's pop that there, and 2 up on the imaginary. Alright, so that there is going to be Z1. Might use a different colour. So Z2, it's going to be -1 on the real axis and 3 up, so let's say here, on the imaginary one. So where those points intersect, that is Z2. And lastly, we have Z3, so we can either deal with it in our exponential form, or maybe what's easier is that we already decided that this was equal to -2 a moment ago in Cartesian form. So let's just say we use it in Cartesian form, that's going to be easier. -2 on the real axis sits somewhere out here. It doesn't have an imaginary part, so therefore it's just going to sit like this, and that would be Z3. So that there would be my answer to the last part of the question. So that's all there is in this particular video. See you in another one.